Quiz Friday, okay? We don't, well, we do have something kind of new to work on, the linear and angular velocity stuff. So we're going to work hard on that today. We're going to spend a lot of time working on that tomorrow, and then the Quiz Friday. So, but a big part of that, doing those problems, is using radian measure. And so getting comfortable with radian measure, what quadrant it's in, converting back and forth, those things will be on there too. Okay, but the problems that are the more challenging problems will be probably this stuff we start today with linear and angular velocity. So I've got two pictures here. So I thought this was important enough to just print this and give you a handout. So I'm going to give you this. No, you cannot use this on the quiz. Sorry, but you can certainly use it to help yourself review. It's probably no different than what you've already put in your notes, but maybe it'll come in handy. So now what I added before, after I printed this, I added this over here. So I don't know if you want to write that. If you want to write that on yours, you know, that was kind of the definition of a radian angle, was the arc length divided by the radius. And so again, radian angles are almost exclusively used in or come from the idea of a circle. Okay, now, you know, when you first learned about sine and cosine, and we're about to get to that after this quiz, so next week we'll start getting into sine and cosine, how that plays into this. But what you've seen with sine and cosine is in a triangle, right, with angles, those kind of angles. We're going to show how sine and cosine could be way broader than that, do a whole bunch of different things, but only really if you use radian measure as the angle and not degree. Okay, so degree is somewhat limiting. All right, so anyway, the definition of a radian, so 1 radian, so if the radius and the arc length are the same, then that's 1 radian. If the arc length is 2 times the radius, 2 over 1, that's 2 radians, and so forth, so on. And of course, we figure out that all the way around the circle is 2 pi. Okay, so because all the way around a circle, the arc length all the way around the circle, that's just circumference, and so that would be 2 pi r, and then you divide by r, and sure enough, so right, so that's why the theta all the way around the circle again has to be 2 pi, and also because of our string, we measured the string all the way around, sure enough, there's about 6.28 of those all the way around, okay? Now, a couple other important things on here. The XY axis, the coordinates that divides up the quadrants, understanding pi halves, pi, 3 pi halves, 2 pi, and also their decimal equivalents, that this is 1.57. Here's 1 radian. You can see it's a little over 1.5. This is a little over 3. This is a little over 4, about halfway between 4 and 5 radians, okay, and so forth. But it's just pi, 3 pi over 2, pi over 2 as decimals. So those are important decimals to kind of memorize, okay? Those are good decimals to know, all right? And then we've got our blue, our radians around the circle. Now, as we get into the homework, some of the stuff I talked with people today about. So if you've got 5 pi 6, and you need to tell what quadrant that's in. I think as you get more comfortable with radians, I think you start to memorize these first quadrant ones. The way I usually think of this, I think of pi 6, I know is 30, that's 180 divided by 6. I told you to get away from converting to degrees a little bit, but these I do. These in my head, this is automatic. 180 divided by 6, that's 30. So pi 6 is 30. Pi 4ths is 45. Pi thirds is 60. So those I do think about degrees. But if I've got to do 5 pi 6, I'm not going to convert that to degrees. What I'm going to do is I'm going to say, okay, that's 1 pi 6 5 times. Okay, so 1 pi 6, 2 pi 6 on my count. Or, more likely, what I'm going to do is this. If I'm looking at 5 pi 6, I'm going to go over here and I'm going to say, okay, well, pi, that would be 6 pi 6. So we were talking about common denominators yesterday. So if I want to know what quadrant 5 pi 6 in, as soon as I realize this is 6 pi 6, I got it. What quadrant? Got to be in 2. It's short of 6 pi 6, right? And it's only, and how short? It's only 1 pi 6 short. And again, in my head, I'm thinking pi 6 is 30. right? Pi 6, 180 divided by 6 is 30. So it's 1 pi 6 short. That's going to be in quadrant 2. It's only 30 degrees short of 6 pi 6. Okay? Same thing if I have 17 pi 6, right? I'm going to be looking at this and saying, well, that's 12 pi 6, right? That's 2 pi. And I go around again, that's going to be 18 pi 6. Sure enough, 17 pi 6 is going to be just short of that. That's going to be in quadrant 2. You know, so that, to me, is kind of the thought process as you go along, as you get used to these radians. So you kind of memorize these first quadrant ones, and then use that to help you get around the circle. Now, I'm not saying that's the only way. If you convert to degrees and that helps you, and you know, if you've got some other kind of method that makes sense to you and that's working for you, that's fine too. Okay? All right. So these are two pretty important pictures to help us kind of get used to these quantities. All right? All right. Any questions on the homework here? Yes?
89.
89. So 89 was the one where 89 and 91, it says, find the length of the arc on a circle of radius r intercepted by central angle theta. So it comes back to this right here. Okay? Now, if we multiply by r, and one of the formulas, I told you yesterday I didn't really want you to memorize formulas. I want you to just kind of think your way through. And the more I thought about it, the more I thought, well, I know there's going to be some of you who feel more comfortable if you've got a formula memorized. If you've got a page of formulas, maybe you make yourself some little note cards or Quizlet or something and you memorize it. That's fine. I don't mind that. That's okay. So I'm going to give you these sets of formulas. I'm going to give those to you. If you'd rather, kind of rely on that a little bit, I'm okay with that. Well, here's a big one right here. S equals r theta. Now, the thing to keep in mind is this only works when the theta is in radians. And that's what you had to do on 89 and 91. You needed to take that degree and you needed to change that to radians. So 89 says find the length of the arc on the circle, radius r intercepted by central angle theta. So you've got 120 degrees. We have to convert that. So what is that? That is 2 pi thirds. Now, I've been doing this for so long that when I do this, when I look at that angle, I'm seeing it as 260s. Remember I said memorize the first quadrant angles? So when I see 120, in my head, I think of 260s. And I know that a 60 is pi thirds, right? Pi thirds, 180 divided by 3. So I know that 60 is a pi thirds, and when I see a 120, I know that's two of those, so it's 2 pi thirds. Okay, but the way we talked about it was to multiply by pi over 180, right? And then reduce. Same thing. Same thing. Okay, so I don't memorize, again, I go back to this pi over 180. I don't use it as much as that, but it's fun. It's fine if you do that. Okay, so that's 2 pi thirds. So what's the arc length? We simply take our radius, 15 inches, times 2 pi thirds, and we get 30 pi thirds, which of course would be 10 pi, and we should probably put units on that. That'd be inches. Okay? There are no units. I think I mentioned this. I said that radians is really unitless. We only talk about radians if there's nothing else there to talk about. Like, for example, if we were doing angular velocity, we're going to talk about today so many radians per second. We'll talk about radians. But in this case, this is 15 inches times 2 pi radians. We're not going to call that inches radians. You know what I mean? It's just going to be inches. Radians is unitless. It just kind of goes away if it's not needed. Okay? And so that's just inches right there. Okay? All right, so 91, while we're at it, we might as well look at 91. 91 is 3 meters times 150 degrees, so S equals r theta. So 150 degrees. Again, I'm going to look at that as maybe 530s. Again, because what do I know are the important angles? 30, 60, 45. So 150 to me is 530s. A 30 is pi 6. So that's 5 pi 6. Or multiply by pi over 180. Right? And you get 530 goes into there, 30 goes into there. So this is going to be 3 meters times 5 pi over 6. So that's what? 5 pi over 2 meters. Would that be Did I do that right? So 3 times 5 power 6. Now, it didn't say how to give the answer, so I'm fine with that. But if you want to multiply that out with the pi button, if you want to, it sounds weird to say 5 pi over 2 meters. If you want to multiply that out with the pi button and get a decimal, fine. Now, the calculus rule, and it really doesn't hurt us probably to start using this. Then you take calculus, you'll be used to this. On the AP calculus test, anytime they give a decimal answer, unless the directions say differently, anytime they give a decimal answer, it has to be out to 3 places. Okay? So I probably won't get too picky on that until we get used to that, but let's just say that if you're going to give a decimal for this answer, unless the directions say differently, let's go out to 3 decimal places. Okay? So if you go 5 times pi button divided by 2 and give a decimal, let's do 3 decimal places. Okay? All right. So that's this formula right here. Seth, does that help?
Yes.
Okay? Yes?
95.
95. 95 says, find the radian measure of the central angle of R that intercepts an arc of length S. So again, it's the same formula. So, but this time they said find the radian measure of the angle. So, now what we're going to do is we're just going to do that. We're going to do theta equals S over R. Okay? So we're going to take S, what'd you say, 95? So we're going to take 10.5 centimeters, and we're going to divide by 25 centimeters. And then just get, that's it.
Okay, because the answer is weird.
Okay, what do you got? Tell me what 10.5 divided by 25 is. 0.42? What's the answer book say?
21 over 50.
Yeah, if you convert that into a fraction, that'll make it.
Oh, okay.
Oh, 21/50. Yeah, 4,200 is 21/50. See, that's weird. I agree that's weird. Here's why. Because I think when I do radians, if I have pi on it, then we do a fraction, like pi halves, 3 pi halves, pi 6, that kind of thing. Okay? If we don't have pi in it, I think a decimal makes more sense. So I'm fine with 0.42, because what picture did I have you memorize, right? Or are we looking at 0.42? So where would 0.42 be? About here, right? About here. Okay? That's what it would be. Okay, 0.42, because that's 1 radian, so 0.42 would be right in there. Maybe about a, 30 degree, 25 degrees, something like that. Okay? Something less than 30. Well, what's pi 6? What's pi 6? Isn't that about 0.5, roughly? 3.14 divided by 6. So it's about 3 divided by 6, about 0.5. So a 30 degree angle is about half a radian. Okay? So 0.4 radian would be a little less. Than that. Okay. All right. Any others? Yeah, I would just decimal. And again, if you say radian, that's okay. If you put radian on that, that's fine. Okay. Because the centimeters cancel, right? See, that's what we talk about radian being unitless. So that's theta equals, and that's S divided by R. Yes, Jack.
You have this number that 1 radian is 57.3 degrees. Do you want us to use that for certain things?
No, we really don't need that much. That 1 radian is about 57 degrees. I mean, I think if you're looking at this picture, it's pretty obvious that's about where it is. It's just short of 60, right? I mean, I don't know that that's ever really a conversion. Because usually when I suppose it could be. Like if I gave you the problem, 3.42 radians is what in degrees, you could take that times 57 but we don't even memorize that out, So that's where I would say if you just do 3.72 times 180 over pi, right? Take 180 divided by your pi button. Take 180 divided by your pi button.
Yeah, it's different.
It's 57.29
29.
something, right? I mean, but that's where the 57.3 comes from. It's 180 divided by 3.14, right? It's divided by pi. And that's our conversion. So you're saying 3.42 radians, each radian's about 57.3 degrees, so take that times 57.3, it's the same as doing this, right? Same as doing this. Okay, what I like about this is it's exact, especially when you use your pi method. Okay, and remember, why would we do 180 over pi? Because radians are going to cancel radians, and we're going to end up with degrees, and that's why we do 180 over pi. Okay, all right. Anything else? All right, let's move on. So, back to your notes here, and we're going to spend a lot of time here before lunch and then even a little after lunch just working some problems together, and then I'm going to give you some for you to work on. Now, the pressure's on you a little bit because this is a little bit personal for me because for 20 years of teaching calculus, the honors advanced math students come in, and there's always a one time a year where it seems, and I don't want to scare you here, there's always one time a year it seems like there's tons of kids coming in for help, and it was always linear and angular velocity. So on the plus side, if you can get through this, I think it's smooth sailing the rest of the year because it seemed like this was just, and so I would always kid Mrs. Payne and my wife also that it's like, oh my God, this is not that hard. Why are they having so much trouble? You guys must be terrible teaching. How can you not? How can this be so hard for these kids? And now I'm teaching it, so it's kind of personal for me that you guys really understand this, or else. It's 20 years of giving them a bad time about this. So I'm going to really try hard. Okay, try hard to get you guys to figure this out. Okay, so that's why I lose sleep over it last night and decided I'm going to give you some formulas. What the heck? So here's what we had up yesterday. Okay, again, at its core, velocity, any kind of velocity, is just something over time. It's something per second, something per minute. So it's dividing. That's what per means, right? It's dividing. So at its core, angular velocity is an angle divided by time. Now, most of the problems we do are going to be radians for our angle. Matter of fact, for angular velocity, I'll just say it, they're all going to be angles. It's going to be radians per second. I can't think of any we're going to do that's degrees per second. Now, I say that, I'll probably be wrong. There'll be one somewhere. Okay, but I think it's almost all going to be radians because most of the formulas we're using only work if the theta is radians. The only one that works if it's degrees is this one. Yeah, right? I mean, if I got something that goes all the way around in a minute, that's 360 degrees per minute, right? That's 360 degrees per minute. And if I want to convert that to per second, I would just divide by 60, right? It's going to be 6 degrees per second, right? 360 degrees per minute. So there you could use degrees. But every other formula we use, the theta's got to be in radians or it doesn't make any sense. Okay? All right. Linear velocity is simply a distance divided by time. Remember we said S? Now we're talking about in circles now. All of our motion is going to be in circles now. Okay? So linear velocity means a distance. So it's going to be inches per second or feet per minute or miles per hour. So we're going to have a distance divided by time. Well, guess what? What's our distance? Our distance is an arc length. And we've already learned that our arc length, just like we were doing earlier here, right here, our arc length is just r times theta, but that only works in radians. This formula here only works if theta is in radians. Okay? All right. So go ahead and write this down if you want to. If you're somebody who likes to have a formula to hang on to, something to memorize, then we want to be real clear about this stuff. So W, it's actually omega. It's actually the Greek letter omega. It's got kind of a curlicue at the top of it. It's basically a W. That is what we're going to use for angular velocity. So it's either going to be degrees per second or radians per second, but most likely radians per second. Okay? Pretty much exclusively. Radians per second. Theta is going to be an angle. Degrees or radians. But again, almost exclusively radians. Okay, so almost exclusively it's going to be those. S is arc length, which is just a distance around on the circle. So it's that red part. It's a distance. So it's going to be inches or centimeters or something like that. R is going to be the radius of the circle. So that's, again, going to be inches or feet or something like that. V is going to be linear velocity. So that's going to be inches per second, feet per second, miles per hour. Okay? And T, of course, is time. So either one of those two velocities are always going to have a time unit on the bottom. And either a distance on top if it's linear velocity or an angle on top if it's angular velocity. be the formulas that would be important that you can use. Now, most of them are just rewritten combinations of each other, right? So it's, again, that's why I say, yesterday I was saying I prefer you just kind of understood what was going on and you can build all these formulas on your own. And I still, that's my preference. But it doesn't hurt to have something to kind of hold on to for kind of security. So S equals R theta. That just comes from our definition of a radian. Theta is S divided by R. So S is equal to R theta. So that's your arc length. So in your linear velocity formula, S divided by T, it might be helpful to think of S as R theta. Right? So we can substitute R theta here. Now remember, in these formulas, theta has to be in radians. The only one it might not be would be the omega one, but okay, you could have degrees per second, but it's got to be in this one. Okay? Now, by definition, in that other page, I told you, linear velocity is always a distance over time. So it's S, it's our arc length over time. And angular velocity is always an angle over time. Okay, so that's just, by definition, what those two things are. Okay, we've had this one before. So what this one does, this one is a combination then of this and this. Right? If you think about it, if linear velocity is S over T, let's replace the S with R theta. Okay, so actually if you want to, you could do this. Right? I just replaced the S with R theta. And now if you look at this, what do you got? You got R times theta over T. R times theta over T. Well, theta over T is W, or omega. So R times theta over T is the same as R times omega. So that's where that one comes from. So they're just kind of combinations of each other, is all they are. And then the other thing in the problem, sometimes they'll talk about revolutions. They'll talk about, well, what if you go around 6 revolutions? Well, that's not an angle at all. But each revolution is 2 pi. So if something goes around 6 revolutions, that's 12 pi radians. Right? 12, so 6 times 2 pi. So we got to understand that one revolution, also 360 degrees, but again, we're going to mostly be in radians. So one revolution is 2 pi. Okay, so if you got that, if you can keep track of those and know what each of those letters stands for, I think you have a good shot at being able to do this. All right, so let's talk about this for a little bit of a warm-up. We did it yesterday. But we'll just kind of do it together here because I want to get through this here now. Find the angular velocity of the second hand of a clock. Now, we just wrote some formulas down. Take a glance at your formulas. Angular velocity of the second hand of the clock. Which formula will we want to have? Which would be what? What was the formula for angular velocity? Theta over t, right? That's what should come to mind. Okay? Find the angular velocity. What should come to mind is theta over t, an angle over time. Okay? Now, the second hand of a clock. Here it goes. Now, the easy way to do it is it goes all the way around. What's its theta? See, you guys haven't trained you yet. Don't say 360. Right, radians. 2 pi. What's the time? 60 seconds. This is the second hand we're talking about now, right? So that's radians and that's seconds. So the second hand goes 2 pi radians in 60 seconds. That would be pi 30ths radians per second. Now, down here it said put all your answers in radians per minute. Okay, so remember yesterday we had this, we had that thing from chemistry class. We want that to be in radians per minute. So what do I need to cancel? Seconds. So I better put seconds up here and minutes down here. Right? Seconds will now cancel, and I'll now have radians per minute. Okay, so what would that be? Well, this would cancel with that and be 2. So 2 pi radians per minute. Well, that makes sense. The second hand's going to go around 2 pi radians every 1 minute, isn't it? Okay, so that makes sense. So we probably could have done that right off the bat. We probably could have done it in radians per minute right away, but it was a second hand, so I was thinking seconds, right? But we probably could have just went 2 pi radians in 1 minute, right? And we could have just had it right there, okay? All right, what about the minute hand? We actually did this in calculus. I'll show you why here in a minute. What about the minute hand? Well, again, same formula. It's going to go 2 pi radians in 60 minutes, right? It's going to take the minute hand 60 minutes to go around. Well, that's going to be pi 30ths radians per minute, which is what we wanted this in, right? So the second hand's going much faster, 2 pi radians per minute. This one's going pi 30ths radians per minute. Now, we had to do that in calc class today. I still got my work right over here. We were talking about how fast is the area changing as the minute hand goes around, and they were stumped. And it was kind of funny because then I said, well, you know how fast the minute hand's going. Now, we have a calculus expression for that with prime, it means a rate. But anyway, theta prime is essentially omega. It's essentially angular velocity. So that's what I told them. I said, remember last year, angular velocity? And then they all groaned. Like, oh. So again, I'm not trying to scare you, but I think it's working. All right, so look what we did. So I said, remember, the minute hand goes 2 pi radians in 60 minutes, right? That's what it was. All right, anyway. And then we can do the hour hand, but we need to move on. All right, so let's look in your book at page 290. You're probably still there. There's a whole bunch of kind of story problems here, starting with 107. Okay? So let's look at page 290, and we're just going to work through some problems here. Okay? So everybody agree on page 290, look at prop 290, 290, there we go, 290, problem 107, go ahead and read it. Okay, so of all of the terms that we've been talking about right here, what are we trying to find out of those terms right there? No, I don't think it has anything to do with movement. I don't think it has anything to do with rotation. Difference in latitude. Huh? Isn't just degrees? Aren't latitudes and longitudes in degrees, right? So we're just looking at latitude. So if this city is here on the globe and there's another city due north, it's just going to be a change in degrees. What's its difference in latitude, right? So this is simpler than getting into velocity and stuff. It's just that. Now I heard somebody say arc length. Arc length would be the distance between them, right? That's how far apart they are. And they do give us that. They say that the Earth is a radius of 6378. So if we look, so the radius of the Earth is 6378. So we got, here's the Earth, here's the radius, 6378, okay? And it says that Syracuse and Annapolis are 450 kilometers apart going due north. So if I go due north, that's 475 kilometers that they're apart. So, aren't they just wanting that right there? What's the difference in their latitudes? Right? It's just the angle between them. So what formula is going to be the one I want? What's that? The top one. Because look what I got. What's 475? S, and what's 6378? R, and we're looking for theta. So I got S and R, I need theta. So I'm going to use that formula right there. Okay, so I'm going to have theta is just going to be S over R, or I could just first plug into it, S equals R theta, right? And so I can put 475 equals 6378 times theta, right? And then I just divide. Or just convert it to this first and then do, right? So we just got to, again, it's just getting comfortable with reading the problem, looking at the numbers, and saying, what are they giving me? Which of these things am I being given, and what am I trying to find? Okay, and if you can put that together, then you got it. Okay, so what's 475 divided by 6378? 0.07. Okay, and that's radians. You guys keep the other decimals. Now, I don't know if it said they probably want it in degrees, because normally we give latitudes in degrees, right? So how would we convert that to degrees? Remember, this formula only works in radians. That's why it gave you that decimal. So what do we have to do to change that to degrees? Times by 180 over pi, right? So take that number that you have in your calculator, keep all those decimals, times 180 divided by pi button. What do you get? Change that to DMS, because latitudes are a lot of times given in degrees, minutes, seconds. 4 degrees. 2 minutes. 33. Is that really? It gives you decimals per second? Oh, I didn't know. Okay. If it has room, probably. Probably if it has room, it does. Right? So depending what they asked for, they weren't really clear in that one. I would be clear in the quiz. Okay, if I wanted it degree, minute, seconds. Understand again that this formula, theta is only in radians. So when you divide S divided by R and you get 0.07, that's radians. Take it times 180 over pi, gives you degrees. Change it to DMS, maybe would be something you might want to do there. Okay, let's move on to, let's do number 110. Let's do 110. Okay? Electric hoist is being used to lift a beam. So what's happening is that drum is rotating and cranking up the chain as it lifts. So that drum is rotating, okay? All right, electric hoist being used to lift a beam. The diameter of the drum on the hoist is 10 inches. Now, we don't usually use diameter. We use what? Radius. So we've got this circle. This is that drum rotating around. Which direction it rotates doesn't matter, okay? And so our radius of that's going to be 5, okay? The beam must be raised 2 feet. Now, let's talk about this. How does the beam coming straight up 2 feet have anything to do with the circle? Say that? So if you want the beam, so as this drum rotates and the chain wraps around it, what happens? If you have 2 feet of chain around the drum, isn't the thing lifted 2 feet? Right? Some of you might have been wondering why we call this linear velocity if we're going in a circle. Think about a bike. We're going to talk about a bike later. Think about a bike and you took the back tire and you just coated it in paint, wet paint, and then you started riding, right? You would leave this trail of paint, right? Well, let's say the bike was, 6 feet around the tire, right? So if you ride and you go one rotation of that back tire, how long is that strip of paint? 6 feet, right? So the circumference, so the arc length on the circle is the distance the bike's traveling, isn't it? Okay, so it's the same thing here. Okay, so if we're lifting it 2 feet, and what would that said it was inches, so we got to be careful. So 2 feet is actually 24 inches. So if we're going to lift the beam 2 feet or 24 inches, which one of these things is that? Come on, there's only 2 things on there that are in inches. No, that's inches per second. That's different. It's 2 feet is inches. 24 inches. There's only 2 things on there that are measured in inches. What are they? R and S. Those are the only 2 things on there that are measured in inches. So what's our 24 inches that we raise that beam? That's S, because it's around that drum, right? As that drum rotates, that chain's going to wrap around, and it's going to lift that thing 2 feet. So we need the arc, we need that drum to go around a distance of 2 feet. That's going to be S, okay? So we just have to identify that. So our S is going to be 24, okay? Question is, number of degrees through which the drum must rotate. So what angle what formula are we going to use? Top one again, S equals R theta. Okay, S equals R theta. So 24 equals 5 theta. They said they wanted it in degrees. 24 divided by 5. Because we had to make that 24 to make things match. In inches. What is that? 4.8 exactly. But that's measured in radians. They asked for degrees. Times 180 degrees over pi, because we want radians to cancel radians. What do you got? 200 exactly. 0.2 degrees. So it's going to have to go around, not a whole turn, okay, but it's going to have to go around. Now it makes sense, because think about it. This drum, to go 2 feet, 24 inches, this drum has a 5-inch radius. 2 pi r is the circumference, right? 2 pi r, so that'd be 10 pi. 10 pi is what? 10 times 3.14, that's about 31. So if it went all the way around, that'd be about 31 inches, right? Well, we only had to go up 24 inches, so we didn't have to go a whole turn. Kind of makes sense. Okay, kind of makes sense. All right, let's go to, let's pick another one. Let's get a linear and angular velocity one going here. Let's go with 112. Let's go to 112. Okay, a carousel with a 50-foot diameter makes 4 revolutions per minute. Like a Ferris wheel, is that what we're talking about? A carousel? Or is that more a merry-go-round? Merry-go-round. Yeah, the merry-go-round. Okay. The little horse, yeah, they go up and down. Yeah, well, we won't talk about the up and down part, but, okay, so there you go, carousel. All right, 50-foot diameter makes 4 revolutions per minute. Find the angular speed in radians per minute. The angular speed, same as angular velocity. Okay, so what's our formula? Angular velocity was theta over t, right? That was the one we had for angular velocity. So this carousel has a 50-foot diameter, so I'm going to write down a couple of these things. So that'd be a radius of 25. We don't care about diameter usually, we like radius, okay, in our formulas. 4 revolutions per minute, 4 RPMs. I usually write it like that though, because I like to remind myself we're dividing. That's why I don't usually write MPH for miles per hour. I'm going to put miles divided by hours to remind myself we're dividing. Okay? So 4 revolutions per minute. Okay? Well, isn't that the angular speed almost right there? What do we need to do? What do we talk about revolutions? Yeah, each revolution is 2 pi. So 4 revolutions per minute, isn't that going to be 8 pi, what? What are the units now? 8 pi radians, thank you, per minute now. See, that's the reason I like RPMs, because R is revolutions, R is radians, which one's which, right? RPMs is usually revolutions, though, so we know that. But it's 8 pi radians per minute. Now, what they wanted in? Radians per minute. Aren't we done? That was easy. I didn't even need the theta over t. I already had it, but that is theta over t, right? That is theta over t. 8 pi is the theta, right? 4 revolutions, that's 8 pi in 1 minute. That's theta over t. Okay, so again, that's why I never really like messing with that formula. It's just kind of common sense. It's an angle over a time. 8 pi radians per minute. If they wanted radians per second, we would do the chemistry thing. We'd get the line, we'd change minutes into seconds. Okay? What's the linear speed? Now here's where having a formula I think is maybe kind of handy. What do we want for linear speed? Which formula maybe do we want here? We got 2 of them for linear speed. Which one do you want, top or bottom? Yeah, 50-50 shot. No, either one will work. But I'm saying the top. Why? We already got that, right? Remember, we just found omega. We just found the angular. So then I like this one. Okay? So now all you got to do is multiply by the radius. So angular, so that's our W. So linear velocity is going to simply be 25 feet times 8 pi radians per minute. Now remember how I said radians just kind of disappear? They're unitless. So what is my answer here? 25 times 8 is what? 200? Pi, and what are the units going to be? Feet per minute. The radians just kind of disappear. Right? Because remember, radians are kind of unitless. We need them when we do angular velocity. We need to say something per minute, radians per minute. 200 pi feet per minute.
Should we keep pi?
I like it, yeah. Why not? Because probably if you go to a decimal, then all of a sudden you got a chance to round wrong or do something silly. So I'd keep it in terms of pi, yes. Sometimes, though, if you want to make sense of it or if you have to explain what's happening or for whatever reason, sometimes a decimal might be good. Because you're right, we don't usually talk this way. You know, how fast is this carousel going? 200 pi feet per minute. Well, that seems silly, but it's like 600 and something, right? It's like 6, because pi is about 3. So it's about 600 feet per minute. Okay, so that's how much distance it's covering if you're riding around on that thing. Okay, all right, so that's a little bit of what this looks like with what's going on here. We'll come back after lunch, we'll do a few more. Thank you. Kind of stick with it. Like that.
Oh, yeah, I would do that.
I just like it.
I mean,
Distracting.
no,
I'm straight.
All right. Okay, here we go. Here we go.
Did you start the recording?
I did. Thank you. Let's go to 115. 115. Read to 115.
He was, I saw.
Well, I understand that. Did you come in first and ask me? I can't remember.
Oh, no, I was trying to waste a little.
Oh, yeah, nice try. Nice try. Well, next time, waste a little more time. Come ask me. All right, here we go. 115. So, car is moving at a rate of 65 miles per hour, and the diameter of its wheels is 2 feet. So when I'm going to read that, diameter of the wheel, so that's the circular part. We're always looking for the circular part of this. So that's 1 foot. Okay, so the radius, because diameter is not part of any of our equations, it's radius that we want. So I see radius is 1 foot. And we've also got 65 miles per hour. Now, which one of our things here is the miles per hour? Linear velocity. The only thing on here that is a unit of distance over time, miles per hour. That's linear velocity. So again, as the tire rotates, right, when the tire goes around 1 revolution, however many feet around that is, again, coat that tire in paint. As it moves 1 revolution, right, the line of paint is going to be how far it's traveled. Okay, and so the distance around converts to a linear speed, okay? So that's linear velocity is 65 miles per hour. So in this problem, V is 65 miles per 1 hour, like that, all right? So we are trying to find the number of revolutions per minute that the wheels are rotating. Now, the difficulty with revolutions is we don't really have a formula for revolutions other than 1 revolution is 2 pi radians. So it's not like a formula just jumps out at us that we would use. But this is so, right, because we've got R, we got a couple of formulas that have R in them, right? We've got V is 65 miles per hour, so we might have something like this, but then that's got theta and T. We want to end up with revolutions though, so here's where, again, I go back to what I said of, I don't like just memorizing formulas because a formula is not always the answer, okay? So thinking your way through it. So in my mind, what I like to do in a problem like this is I'm going to go 65 miles 1 hour, and I'm going to try to end up with what? What do they ask for? Revolutions per minute. So I'm just going to take 65 miles per hour and start canceling units until I can get revolutions per minute. Okay, now there might be other ways we could maybe use the formulas, maybe that would make more sense to you, but I think this is just a pretty good way where you can kind of do the same thing about every time and get this. So we're clearly going to need to get minutes down here, so hours to minutes would be a pretty good easy combination. So 1 hour is going to be 60 minutes, okay? So we want hours up here, we want minutes down here, hours cancel, 60 minutes in 1 hour. So now we need to get revolutions. Well, we probably need to go, so if we go revolutions, what is if our radius is 1 revolution is going to be how far around this thing? 2 pi, yeah, it's 2 pi radians, but 2 pi r is circumference, right? 2 pi r is circumference. So 1 revolution, and we could even put that, we could even put that back here. 1 revolution is 2 pi radians. It's 2 pi r distance, whatever our distance units are, right? It's 2 pi r distance, okay? Because what do we sometimes want? We sometimes want radians per time unit. We sometimes want distance per time unit, right? And so maybe we say, okay, it's 2 pi radians, but it's 2 pi r distance. 1 revolution is a circumference, okay? And so whatever our distance is. So in this case, 1 revolution is 2 pi feet, right? So it's 2 pi times our radius of 1 foot. So 1 revolution is 2 pi feet. So that's how I can get revolutions into here. I can get 1 revolution. Remember, we want revolutions on top. And that was what? 2 pi feet. Now, maybe that was a little quick to put that in there because I don't have anything that can cancel right now. Remember, I want to end up with minutes, and I want to end up with revolutions up here, right? I want revolutions per minute. So what do I need to get canceling here? Miles and feet, and I can do that in one fell swoop. I can get feet here. I can get miles down here. That's going to cancel miles. That's going to cancel feet. So 5,280 feet in 1 mile. And now I've got all that stuff canceling, and I'm left with revolutions per minute. Okay? So at the end of the day, many of these problems can be simply done with look at your given information and look at what you want to end up with for units, and then make it happen. And it's all about multiplying and dividing. Okay? And so whatever that comes out to, I don't know what I got here, 910.37, does that sound right? That's what, I didn't work these out, this is kind of here. All right, so what does B say? B says, find the angular speed of the wheels in radians per minute. Okay, well, we could actually just take one more step, right? We already got minutes here. Okay, so let's get radians to end up here, and let's get revolutions to cancel, right? So now let's cancel revolutions, and now we're going to end up with radians per minute. So what do we got? 1 revolution. What is it for radians? 2 pi. 2 pi radians, 1 revolution. 2 pi radians, 1 revolution. Okay, and so now we end up, so all we really have to do is then take that number. And we kind of know that. You didn't need to do it there. We talked about this. 1 revolution is 2 pi radians. So if we just came up with 910 something revolutions per minute, each one of those is 2 pi, so you just multiply by 2 pi. Okay, but it works out doing it like that. Okay, all right. Let's talk about 114. Okay, so let's look at 114. A 2-inch diameter pulley on an electric motor that runs at 1,700 revolutions per minute is connected by a belt to a 4-inch diameter pulley. Okay, so what we end up with here is we've got a small pulley and a larger pulley that's twice as big. This one is 2-inch, this one is 4-inch. Okay, and it's connected by a belt. Now, we're going to talk about bikes here in a minute. This is very similar to the bike problem because you got your chain, right, around the 2 gears on your bike. All right, so the electric motor this is the motor here, right, and this is the saw here. Okay, all right, and so find the angular speed in radians per minute of each pulley. Now, it says that the small pulley is going 1,700 revolutions per minute. Okay, so what do we know? And this is what we're going to talk about the rest of the time with the bike. We're going to talk about a bike scenario. How fast, let's do revolutions, is the big pulley going? Do you think it's double? Or is it half? Revolutions. I'm just talking revolutions right now. Isn't it going to be half? So when this goes around, just imagine a point right here. When it goes around one time, the belt is going to go this far. Well, that's only going to be half of this, right? Because this would be 2 pi times 2. That'd be 4 pi. This would be 2 times 4. This would be 8 pi. So if this goes around, that would be 8 pi circumference. Excuse me, what I say this was 4 pi, 2 pi r. So this would be 4 pi. When this goes around 4 pi, that's only going to be half, right? So this one's going to go half a revolution. So when this one does 1,700, this one's going to do half of that. So this one's going to be 850 revolutions per minute. Okay, so now we just came up with something important there. It makes sense. The bigger circle is going to go around, right? It's not going to go as many revolutions. Linear speed is the same, right? Both of these have the same linear speed because that's the belt. That's the distance on the belt. It's kind of like the tire moving and leaving the paint strip along the thing. That's its linear speed. Yeah.
It says 2-inch diameter.
Ooh. Are they both diameter?
Yeah.
Oh, shoot. Okay. Well, yes, but as far as this goes, yeah, that is important, though. I'm glad you said that. So this would be 1, this would be 2. But it's still 850 here, right, for revolutions. Still half. Okay, now, so we want the angular speed of each one. So that's not the angular speed. Angular speed is measured in, get away from degrees, radians. Most of the time we want radians per minute, right? So it's simply going to be 1,700 revolutions per 1 minute. And then it's going to be, we want revolutions to cancel. And we want radians per minute, so 1 revolution is 2 pi, so we're just multiply by 2 pi. Now again, you don't have to set it up like that. We said 1 revolution is 2 pi radians, so 1,700 revolutions is going to be 1,700 times 2 pi. So 3,400 pi radians per minute. And then the other one, same thing. You're going to multiply that by 2 pi. And that's going to be 1,700 pi radians per minute. Find the revolutions per minute of the saw. We did that already. Find the revolutions per minute of the saw. And we did that. That was 850 revolutions per minute. It was half of that. Half of that. Okay? All right. Now, so let's go to the bike. So let's talk about 119A. Okay? So let's look at 119A, and that's going to be closely related to what we just did. Okay? So the radii of the pedal sprocket, which is your front sprocket, that's the one controlled by the pedal. So as you go around, that front gear goes around, and then the chain makes the back wheel go. Okay, and so the bicycle it's 4 inches on the pedal sprocket, and it's 2 inches on the wheel sprocket, and the wheel itself is a 14-inch radius. A bicycle is pedaling at a rate of 1 revolution per second. Okay, so we're just going to do part A. Find the speed of the bicycle in feet per second and miles per hour. So let's just do feet per second first. All right, so find the speed of the bike. So we need, if you look at what we need here, right, speed of the bike was going to be which one of these? Which one of these is speed of the bike? Speed. And at this, oh, V. I'm sorry, I thought you said feet. I thought you said feet. V. V is the linear velocity. That's what we're looking for. Okay? So we have several different things here, right, that we could use for V. But now, what's different about this is we got several different circles going on. We got this one, which, what was that, a 4-inch? Is that 4-inch diameter or radius? That's radius. Okay, that's 4. We got a bigger sprocket. No, it's smaller in the back, isn't it? Smaller in the back. Okay? And so that was just 2. This one's a 4-inch radius. Okay? And then, of course, it's connected to the big wheel, which we said was 14 inches. Okay? So what we got to do is we got to see how this is turning to get our speed of the bike. But all we know is how fast this one is turning. And the bicyclist is pedaling 1 revolution per second. So this small sprocket is 1 revolution per second. Okay? So now what we want to do is we want to go to this sprocket. How fast is this sprocket moving? Or that gear? Isn't it going around twice in a second? Okay, because this one is bigger. You pedal all the way around. That's going to cover this distance. Well, that's going to be 2 times around this one. If this sprocket goes around twice, what's the wheel do? Goes around twice. You see how that's connected? So when you pedal around 1 time, your wheel is going to go around twice. Well, how far is that going to go? So this is where you see what I'm doing. I'm not using a formula here. You think your way through it. I think that's way better on this one because I think the formulas are very confusing. Okay, now I can show you what that would look like, but how far does this wheel go if it goes around twice? 2 pi times, remember circumference is 2 pi r, right? 2 pi times 14. Right? So if this sprocket goes around once, this one is going to go around twice, which means the wheel's going to go around twice, because that's what it's connected to. And if the wheel goes around twice, then it's going to be this times 2, right? Because this is the circumference of the wheel, so that's the distance around. If it goes around twice, you got to multiply that by 2. And we get what? 56 pi. And what are the units going to be on that? That would be inches. Now let's talk about why. Because this is inches, right? This is inches, right? This is circumference. So this is in inches because this is 2 pi radians and that'd be 14 inches. So this is just inches times 2, just 2 because it goes around twice. So that's inches. And that does that in, remember, we just pedal 1 time around every, what did it say? We're doing 1 revolution per second. So this is going to go around twice in 1 second. So what we just found is inches per second. Okay? So this goes around once in a second, means this is going to go around twice in a second. How far did it go around? It went around 56 pi inches in 1 second. That's how far the bike's going to travel. We just found the speed of the bike. Now, they first wanted it in feet per second, so we got to keep going. So how do we convert that to feet? Well, there's 12 inches in 1 foot. So we're going to do that. So that's going to be the feet per second, whatever that comes out to be. Okay? And you can divide that out. And I've got that here, I think. 14 pi over 3, or you can get a decimal if you want. That'd be feet per second. Then they want miles per hour. Well, how do we change that to miles per hour? We're going to get rid of seconds, right? So we're going to go, how many seconds in an hour? 3,600, 60 times 60 seconds in 1 hour. Okay, oops, that's hours. Okay, so that's going to cancel seconds. So right now we got, and then we got to cancel feet. Now I'm out of room. Let me work on magic here. All right. And now we got, and we want miles, so we got to get rid of feet. So 5,280 feet in 1 mile. So now feet are gone. So now we're down to miles per hour. Okay, so 56 pi times 3,600 divided by 12 divided by 5,280. Whatever. Okay, I've got, well, she's got roughly 10 miles per hour, approximately. So. Okay, but I didn't really use a formula. I just think sometimes on problems like this, using a formula is not really the way to go. I mean, if you wanted the linear velocity of that tire, the formula we have for linear velocity is this, right? Okay, that's fine. So we have that for linear velocity. So the radius, of course, of the tire is 14. The radius of the bike of the tire is 14. But then what's the angular velocity? So you still got to come up with that. Okay, well, what was angular velocity? Well, that was theta over t. Okay, that's fine. But you still have to come up with how many radians that went around per time. So you still have to say to yourself, okay, this went around once. Means this is going to go around twice. So that's 4 pi, you might say. Okay, it went around 4 pi. So you could say, okay, that's 4 pi in 1 second. Okay, so you have 14 times 4 pi. Well, look what we had right here. Same thing, 14 times 4 pi. So if you want formulas more, you could have done this. Right? You said, okay, omega, that's theta over t. So what's this tire doing? It's going around twice. You still would have to figure that part out. It's going around twice. That's 4 pi in 1 second. And so the formula kind of way of doing it would have worked. Okay? All right. Get your Chromebooks out here real quick. And I've got a link. If you go to Google Classroom, I've got a link here. Says the bicycle activity. Now you don't have to, I made an assignment, don't worry about hitting done or anything, you don't have to, it's not really an assignment, it's something you can go to play around a little bit with this concept of the gears on the bike, okay, and understanding how that works. You know, so when you're riding a bike, when you're in well, I always get confused, what's a low gear? When you're pedaling really fast, is that a low gear?
Yeah.
Is that a low gear?
Yeah.
I think that's a low gear. I mean, I ride a bike a lot, but I still don't know this. Okay, so
It's like 6.
yeah. So low gear goes really fast. I just call them easy gears and hard gears. But so the low gear is when it goes really fast. Well, that's when you got the chain on the little sprocket in the front, right? And so every time you pedal, that just goes around. That just goes around a lot faster, right? Now. So if you've got that, if you've got it on the small sprocket in the front, you can pedal a bunch of times before the tire ever goes around one time, right? You don't go very far, especially if you have it on the big sprocket in the back, okay? So all of a sudden you're pedaling, you pedal 5 times, and the bottom or the back the wheel may only go around once. Right, so you're pedaling a bunch and it's not moving very far. Now you reverse that, put it on the big sprocket in front and the little one in the back. Now all of a sudden you barely go, and all of a sudden you don't even do half a revolution and the tire's already went around once or twice. But it's a lot harder, but it's going to go faster. Going to go, okay. So that's kind of what this is showing. So is everybody getting this to come up when you go to it? Is this showing up when you go to this activity? Okay. Now, free ride, if you click on free ride, so right now, so you can click on these different gears. So the 2 gears are the same. So, and it's going to go by half a pedal, half a rotation. So if I click on the green pedal, it's going to go around once. Now watch this red dot on the tire, and you click, it's going to go around once, and the tire, or it went around half of a rotation, and the tire went around half a rotation. Okay, and up here, how far did your bike go? It went half. So you click on the pedal again. Okay, so when you have a 1-to-1 gear ratio, that's what's going to happen. So now let's do the situation we said where you got the little gear in the front and the big gear in the back. Okay, now, and let's hit reset. So now when you do half a pedal, watch how far the bike goes. It doesn't even go half a way around. Okay, it goes 2/3 of a way around, right? Or I'm sorry, it's because we're only half, it'd be 1/3. It only went 1/3, right? Because we did half a rotation. We go again. Okay, so we went a full rotation on this, but this one's only went 2/3 of the way. It's called a 2-to-3 gear ratio. Okay, all right, and then you can keep going and you can see how that works. Okay, hit reset. Now reverse that, put the big sprocket in the back and the little one here. And this is what we're talking about with a hard gear. Okay, because now you go around half, look how much the tire goes. The tire went around a full 2 times. Half a pedal, and the tire went around twice. You moved quite a bit. Okay, because this thing just went around half, that's a whole bunch of times to go that same distance. Okay, because these two have the same linear speed. All right, but their angular is much different. All right, we go one more. Okay, so we went 4 units with 1 pedal because it's a 4-to-1 gear ratio. Now, the game part of this, it was kind of fun, and these are easy ones here. If you go to choose route, so like odd man out, you're trying to hit these flags. I should turn up the sound. So exciting. Well, I think the sound is. So you want to hit those flags. So I want to go 1. Okay? So what do I have to set my gear ratio at to go 1? Now remember, I'm only going to go half a pedal, and the par is how many times you have to go half a pedal, right? So 2.5 pedals. Okay? So when I hit it, it's going to go half a pedal. So at half a pedal, how can I go 1? What would I need? 20 here? No, 20 here and 10 here. So half a pedal, this goes around half, that should go around 1, shouldn't it? Okay, so watch what happens. So you hit the pedal. You hear that? Does yours make noise? Give your sound up. Now I want to go from 1 to 3. So now I got to go 2. If I'm going to do this, right, it's kind of like golf. I want to do this in 1 shot every time. There you go. There you go. So if I want to go from 1 to 3, I want to go 2. So now what do I need to do? I better go 40 and 10. So this goes half a pedal, right? This one's going to go around twice. Okay? Now that's pretty easy because each flag is only 2 apart. Now you get into some of these hard ones. And you got to do this. I mean, and now the fractions really get tough. Okay? Matter of fact, I was playing around last night. I did a couple of this, and I was like, oh, God. So I gave up. I gave up. So the biggest point of this is really just to kind of get used to that idea. So if we have a problem like 119 or whatever, you understand, okay, when I pedal this many times, the wheel's going to go around how many times, right? That's the connection we need to make. Okay, if I pedal this fast, how many times is the wheel going to go around? And because then that's when we can get our speed, our linear speed, the speed of the bike and stuff like that. So this can just kind of get you used to that scenario. Okay, all right. So I had one last thing on here, but basically I can show you this again tomorrow, but basically this is click and clack. I don't know if you ever heard of this, but it's guys in the paper, the automotive, people writing automotive questions. My wife's kind of a gearhead in her family, so she reads these all the time. So that's where she got this. But anyway, they're talking about the differential. I'll be honest, I didn't even know how this worked in a car. But it says that the differential is set so that your tires rotate differently. In other words, when you turn left, And think about this is exactly what we're talking about. The inside tire has to go slower than the outside tire. Right? Because same thing, we talked about whipping around. The people on the outside gotta go faster. So that the right-hand tire's gotta go faster than the left, otherwise you'd be skidding, right? And that the differential is what controls that. Well, that's exactly what we're talking about with linear and angular velocity. Okay, so that was something that she had found that she was looking at. All right, so here's your homework, which is going to be a little bit of conversion, coterminal stuff. So the optional part of your homework is play around with the bike thing.
Yay.
Play around with that.
I don't know how to ride a bike, so this is the best one I've ever did.
All right, so this is your homework, so a little bit of coterminal and radian stuff. But then some problems at the bottom with this linear and angular velocity stuff. Okay, we'll check those over. Come in the morning if you got some problems, but we'll probably check over them a little bit too. And we'll just kind of review everything a little bit tomorrow and quiz on Friday. Okay?